this computer because I have an appointment close to the end. So I'm not going to run. I'm simply going to cover less material. Okay. So let's get into the subject. This is our small review. We were looking at the Schrödinger equation in one dimension, and we were looking at our first system was an infinite potential well with this value u here, u naught, going to infinity, and that had a special requirement for the wave function that is a solution to this kind of potential. We understood that the wave function is not really a measurable thing. What is really an important value here is the square of the wave function. So the square of the wave function means the probability of finding is proportional to the probability of finding the particle in a certain position in space. Okay, so for this particular, I don't recall if we actually reviewed this already, or I have some, but I'm going to go through it fast just in case. So for this type of potential, then the wave equation is going to be equal to exactly this one. If I'm just looking to bound states, so to states between 0 and u naught. So in general, the energy is smaller than this value, and so between 0 and L. So this is a very important thing. This is the equation. So the equation is simply k squared here is a positive value, and so we get the oscillatory solutions just as a sine and a cosine. Okay. We do have the problem that since I wouldn't say the problem, it is a feature now that we cannot say that the value of the wave function is 0 here and here, because the potential is not infinite. So really the condition that we should impose on the wave function is the continuity of the wave function and of the derivative of the wave function at this boundary here. So we actually have a differential equation that is a second degree, which requires the continuity of the first derivative. So imposing that, we can get something about, this will be the equivalent of the boundary conditions, of the extreme boundary conditions that we saw in the case of infinite potential well. Okay, so here will be a slightly different. So we have to use the continuity of the wave function and the derivative instead. And now we would like to see how's the Schrödinger equation in this region, in the region beyond the negative values of x or positive values of x beyond L. Okay, so in that case, we have to add the u naught to the equation. So this will be the way to actually describe it. So if u naught is, you can see the difference here. The difference here is that the equation has plus k squared, and the equation here has minus kappa squared. This solution here is a combination of exponential of complex e to the I theta something, and a linear combination of e to the I theta will give you sine and cosines. And the solution to this is simply an exponential that decays as a function of x. Okay, so the solution in this case and in this case will be exponentials, and I say decaying exponential because I'm thinking on the boundary condition, the additional boundary condition, that the probability should not be infinite at infinite values of x, meaning the sensible solution is not something that it's almost 0 here and infinite, for large values of x. What we are asking is that most of the particle would be around this place and there will be nothing here. So essentially it is phi of x will go to 0 in this direction and in that direction. And when we do that, we choose sort of this shape of solution, something that is, you know, exponentially going to 0 in this direction, exponentially going to 0 in that direction. And in the middle here, oscillatory. When is it oscillatory? When it makes sense to define a kinetic energy. In this sense, it doesn't make sense to define a kinetic energy here. Even you can apply the kinetic energy is proportional to the second derivative of this thing. And so the second derivative of this exponential here will be almost dead, will be almost nothing, okay? So this is the important value where you have changes in the second derivative. This is where you have kinetic energy. This is where you have the oscillatory solution, and here you only have exponentially decaying solution. This solution is rather different from what one would expect from Newtonian mechanics. In Newtonian mechanics, if you have a particle at this potential level, it will never go inside the barrier. And here it does. You know, it penetrates inside. Why does it penetrate inside? Because it's a wave, and because of the uncertainty principle, you can actually find out that within the, depending on the distance of the energy level within the well with respect to the depth of the well, this thing will be highly or smaller penetrating function. If we are very far, if we're very close to the origin here, this will sort of die very fast. And if you're very close to U0, it will be sort of a long exponential here. So that means somehow the wave equation is sensitive to the uncertainty principle there, okay? Because it's a wave, okay? So there's a probability. So the energy is not very well defined. If the energy is not very well defined, if there's uncertainty on the energy, well, you could be, you know, getting a bit on top of here, and this is what is reflected on this exponential decay. You don't want to go to the math. Well, you might. You know, if you're you know, a crazy physicist, you might want to go all the boundary conditions in this place and this and match them one pam pam. And when you do that, you find out that there are only a certain number of energy values that will fill the well here between the values of 0 and U0. Okay, so there's a definite small number. Okay, it will really depend on how deep this thing is. And here I have an example. The depth of the well in this case is equal to 6 times the energy of the infinite potential well. Okay, the energy of the infinite potential well is E1 dW, that one. And if this was an infinite potential well, the first energy level would be here. So for this potential well, I said take this value, multiply it by 6, and build this new potential, which has the value U0 in this place. And as you can see, there are only three discrete levels of energy between 0 and U0 that could actually hold a particle in this potential. So if you have a higher energy, well, this will be a traveling well here, traveling wave. It will be near the continuum, and you would not have something like this. Look at the other feature here. The closer you are to the ground level here, the penetration is smaller. Okay, well, when the difference between this guy and this guy is very high, it happens that this constant is very high. If this constant is very low, which means a low difference here, the chi-square is small, so this thing will slowly move there. But if the difference is high, this dies very fast. So we're seeing here the exponential features. The wave functions for large values of x goes to 0, and you have discrete number of levels inside this potential well. This is absolutely different to Newtonian mechanics, where you could actually find any value of energy here in a continuum distribution, and you will always, define whatever value you want for the energy, and you'll see as that the particle will live in this potential well very easily. You will also have the possibility of putting zero energy to the particle, meaning standing at it in the floor here without moving, and that would not violate any law, but quantum mechanically it does. It cannot be. It does have a small amount of energy. If you compare the macroscopic properties of a particle with the dimensions of the well and whatnot, you'll find out that this value here is very, very small compared to actual microscopic values of energy. So you wouldn't be violating anything by doing that. There's going to be an uncertainty in the velocity different from zero, which is so tiny that you're saying, well, this thing is equivalent to be standing up. Okay. So if you now square the wave function, it becomes more evident, because this is the probability of the particle. So the particle lives, mostly inside the well for these three energy levels. These are the three allowed energy levels. If you go to the fourth level, it will, produce an energy around here, up here. So that will be an unbounded particle. This is a bounded, so you only find a finite probability around the region between 0 and L, and that's where the particle will live. So this is what we call a bound state. Okay, so the particle is trapped in this potential. This essentially could be an atom. An atom is something like this. You have a positron and an electron, and the electron is sort of trapped very close where not a positron, a proton, very close where the proton is. Okay, a positron will also do the same trick, but it's not what I meant. Okay. So, and again, the decay is very fast when you're far from the top when your energy level is far from this top, and when you're very close to the top, the penetration to the barrier is quite wide. So you can start looking at this. So the wave function penetrates. So what would happen if I actually cut the potential here down and let the, if I have a particle here and I lower the potential, this particle can actually go through quantum mechanically. Well, to actually describe this, we're going to consider a potential that does exactly that. Okay, so we have this is a classical picture. You have U of X in every space, and you have the E1. With energy E1, the particle will only have enough energy to arrive to this point here, where this is U of X. The blue line is U of X. E is the total energy. The potential energy plus the kinetic energy, which is the difference between the blue line and the dotted lines here, is kinetic energy. So kinetic energy plus potential energy gives you total energy. Okay, so this is the total energy. When the total energy is equal to E1, the particle will only arrive to position A. What happened at A? At A, all the energy of the particle will be equal to the potential energy. Hence, the velocity of the particle will be 0. We'll be standing there in the side of the slope with 0 velocity, and what will happen? Well, we'll feel the force produced by the gradient of the potential there, and we'll be going back. So it goes there, it gets to there, and boom, goes back. So the maximum amplitude that can get some particle with E1, it will be only A. The only way to go through the top of the potential barrier, as it is here, is that this particle, overcomes a bit the level of the maximum energy of the barrier, and in that case, the particle will go through to the right of the top of to the right of the maxima here. Okay, so this is the energy the particle is required to have in order to go through the across the barrier. This is not the case in the quantum world. You know, you can penetrate a barrier with a certain probability, and you can a particle that has only an amplitude to be there in the left side because it has an energy E. It will have as we know, it will have an exponential decay constant here, but it would not be zero here. It will be very close to zero if this thing is very wide, but I can arrange for it to be very narrow. So there's going to be a tunneling probability for something that strikes this potential barrier. Okay, essentially, you will have an amplitude here. Let's say I prepare a beam of particles and I shoot them this way. They all have certain kinetic energy. They come flying into this thing. They decay a bit, and some of them will actually tunnel to the other side of the barrier, despite the fact that their energy is below U0. Okay. So I'm expressing up there what I already told you is something like this is a possible wave function that does this thing when it gets to a barrier here. There will be an exponential decay in this. This must be something like a diagram that we're talking about the real part of the wave function. So let's not worry about the complex components of the amplitude. But the fact is that this thing is actually decays to a finite value. So if the beam of particles is prepared coming from this direction, there's going to be a finite probability of finding at the other side some particle, which in the classical picture will never happen. Okay, so the tunneling probability, this again, it's not a simple matter to actually do all the boundary conditions for something like that. You have to match the wave function and the derivative here, match the wave function and the derivative there. And when you do that, and you say the transmission probability is essentially the in this particular case, the ratio of the amplitudes square at this particular point. Well, no, you want it there, okay? So you're saying this thing has an amplitude and this thing has an amplitude here. You take this amplitude square, take this amplitude square, and you're saying the amplitude of hitting the barrier will be a square, and the amplitude of leaving the barrier will be b squared. B squared over a squared will be t. T will be the transmission probability, which is a factor g. This comes directly. If you are patient enough, you can actually calculate this. I'm not asking you to do that, but you may want to do that. K is simply this. What is that? This is the actual decay constant on the equation. So you'll get an equation like so, like what? Like this equation. So the k squared is equal to that thing. This thing is equal to the k squared. So essentially, this is what I'm seeing. U0 minus e there. Perfect. So the e is below the value of U0. So this is a real number. It's not a complex number. Okay. So this is the way to write the probability of tunneling, which decays with this 2k constant as a function of the width of the barrier. So one can actually measure that. You know, you could actually invent something that has a barrier of different length to actually measure something like this. And the question is, do you actually see some sort of tunneling in some sort of phenomena in real life? You know, and well, obviously the answer is yes. Otherwise, I wouldn't be saying it the way I did. And here I have an example. This is a microscope which was invented in the 80s. So by the time I was actually leaving grad school, and the guy came up with this. I was studying surfaces and the structure of surfaces at infinity. using ion beams and big machines, and these guys came with this huge, with this beautiful small microscope when they have a very sharp tip in a metallic tip, and they mounted this thing on top of piezoelectric material. A piezoelectric material is something that deforms itself if you apply a voltage. So the deformation is very linear, meaning a higher voltage is a higher deflection of this piece, and exactly that can be done to actually move this tip on top of a sample like this. So this image over here is built by swinging, let's say, the Y voltage in this direction, applying a little bit of a step and measuring in the other direction while swinging the voltage. So you apply these different steps, okay, in this direction and that direction. So you can actually sweep this region perfectly well with controlling the deformation of the piezoelectric material, okay. And then comes the other trick. The other trick is that we're going to pass electron through vacuum. Here, this is the vacuum tip, and this is the tip. This solver is very sharp. It ends up being only one atom here, and you have the material down here that has you know, distances that are atomic level distances. So essentially, every one of those, you know, singularities that you see here is coming from the electronic density of an atom. So we were taught at the beginning of the course, or we have always been taught, that you can never see atoms. And here it gives you the impression that you're seeing, well, you're not seeing them because these are not photons. These are intensity produced by electrons, okay? And the way this image is taken is you apply a difference voltage between the tip and the sample. So both the tip and the sample must be metallic. And then you set this loop in a way, you know, put the tip in close proximity to the sample, enough so you will end up having a current here. Okay, there's a standard technical procedure to do that. Let's not discuss it here. Essentially, you are in tunneling. So you apply a voltage and you are having a current here. And then what one can do is tell the microscope to do this raster scan while keeping the constant current. We want the current that goes through the tip and this place to be constant. For that to happen, meaning this is very sensitive to position, so the microscope should move the tip a bit up in order to, when it goes through a region of high density, electronic density, and when it goes to a region of low electronic density, it should approach it. And the mechanical response of this is fabulous, and this is what you get. You get an image with a corrugation, with atomic corrugation, exactly that. You can actually see further deformations of the surface. The gold 111 surface, which is this image here. This is a fake color, by the way. It's not yellow because it's gold. You know, you can make any image look like this. What you're actually plotting here is the deformation of the Z piezo as a function of the position, XY positions in here. And you can see not only the atomic resolution, you can see the reordering of the atoms in a microscopic scale, what is called the herringbone reconstruction of the surface of the world 111 surface. So this is fabulous. This can only be achieved because the current that goes between the tip and the sample is very exponentially sensitive to the separation. So we can use this as a control variable to actually control the position of the tip on top of the sample while scanning. Okay, so this is a fabulous instrument that has allowed learning many things about the physics at the atomic scale, and probably it will be linked to the smallest qubits. The qubits are the future of quantum computing, computing not based on silicon electronics, but something with many parallel roads, and you know, it will take a while for me to do a lecture on that, but it's linked to quantum mechanics. It's obvious. And the devices that are probably going to be used will be in this scale. So the quantum tunnel will have an clearly impact on that matter. Okay. Let's get out of here. I like it too much. Another way, another branch of physics that also see the effect of tunneling is nuclear physics, and this has to do with particles that are with nuclei that actually are unstable and emit alpha particle. An alpha particle is a helium, a fully ionized helium atom, meaning we're going to get there and recover this, but the helium atom is one of the most stable nuclei in the whole periodic table. Okay, so when you find a helium inside a nucleus, a nucleus is a bunch of protons and neutrons, and all of a sudden you can, the wave equation of the complete complex system could be such that you generate something like a particle, which is a helium particle with no electrons. And that is what we call an alpha particle. And that alpha particle can actually go away if the nucleus is too high you call this nucleons. Nucleons are the particles inside the nucleus. Okay, if you have too many nucleons, this is unstable material that wants to get rid of some of the nucleons to find its stability, and for doing that, an alpha particle will have to penetrate this is the very strong potential barrier of potential well of the nuclear interaction. Nuclear interaction is attractive, and it's very strong compared to gravitation and electromagnetism, and that keeps the positive charge of the nucleus bound together very tightly in here, despite the fact that the positive charge of the nucleons are repelling in themselves. But with very large nuclei, what happens is that these alpha particles can sort of get away from this and the alpha particles somehow lives in a bound state around here inside this potential well as an alpha particle. And to go out, we have to tunnel through this. This here, this line, it's the repulsion produced by the two electron charges that the alpha particles has with respect to the nucleus. So, and you will have a repulsion because essentially the everything here is positive or neutral, you know. So if I separate a fraction of this thing out of the nuclei and I put it here, there will be an electromagnetic interaction over this range. The nucleons that are here will not feel the very short range nuclear interaction induced by this big nuclei. They will only feel the electromagnetic interaction between the residual nuclei and the outmoving alpha particles. So this is why this thing looks like a potential interaction of being repelled by by the electrostatic repulsion, as it says here. Okay, so this is a phenomena where this is a situation where you can also observe tunneling in systems like this. Yeah. Okay. Another interesting system to look at is something that looks like a potential, well, like a harmonic oscillator. This is the spring and mass system. See? If you have something that has a potential energy that looks like the blue line here, that's 1/2 k x squared. That thing here is the potential energy of a spring. Okay, and so if you take the derivative of this potential, you can find the force on the spring, which is kx. Okay, so this is sort of the thing. And again, if in a system like this, macroscopic physics, if you have a certain energy level here, it means that if the particle is in this position here, this would be the total amount of energy which is conserved, because there's nothing that in this system can take energy out. The kinetic energy will be the value from the blue line to the energy level E, and the rest will be the potential energy. So this will be the potential energy, and from here to here will be the kinetic energy. The sum of the two is the total energy, which is a constant of the motion. And then the thing what we'll be doing is moving back and forth until the potential energy equals the kinetic energy and arrives to this point. But in quantum mechanics, we know that that's not true. And we can actually guess how the wave function for this particular case will look like based on what we have done before. Okay, we know that in this region where we have makes sense to define a kinetic energy, this thing will be oscillatory. Okay, and in this region over here, it will be decaying exponentially. Perfect. You know, we can now solve Schrödinger equation just by looking at it. Okay, there is a question that you need to actually add the complex component, complex in the sense of a complex numbers, you know, of the unit of complex number I. So what I have just said, you really have to be very careful to actually include the proper values of I everywhere. But essentially, this is the equation we want to solve when we go to a Schrödinger equation. And for the harmonic oscillator, we have the kinetic energy term, we have the potential energy term, and now we are looking for what are we looking for? Stationary state. We have already replaced the IH bar derivative with respect to time of the wave function by e to the phi x, where we have used the standard way of doing that is saying that the time dependence is e to the minus IET over h bar. Okay, when we do that, this is the way the space-dependent function Schrödinger equation turns out to be, and phi of x is only function of the coordinate x. It means that these are stationary states. The probability are not changing with time. Okay. Well, I told you before that there are very many different possibilities to actually having a decay, and the good one is the one that I already mentioned. It's an exponential decay. So this is the position A. This is where the particle will arrive classically. Here it will be oscillating, and from here on it has to decay. It cannot oscillate anymore, and the decay should be something like that, meaning at infinity, this thing should be zero. It cannot cross the axis down. It cannot go up. A and B and C are not, suitable solutions for this problem. Okay, so when you go through the algebra of solving this equation and finding a solution, there are different techniques for doing that. I'm not interested in you doing that part. I'm interested in that you understand the solution. The solution is the following. It's a very simple and very nice one. The energy levels of these systems as a difference with the infinite quantum well increase with n. It does not increase with n.5. Okay, and I'm sorry, it doesn't not increase like n squared. Okay, it increases with n. When n is equal to 0, there is an energy. There is an energy E0, which makes sense also because we cannot freeze everything. The thing has to be oscillating at the smallest level that it can do in order to fulfill the uncertainty principle. Okay, so this is sort of the nice diagram. Now the difference between consecutive level is a fixed number, is simply h bar omega. That's the difference between all the energy levels, which is different than the case of the infinite potential well, as I told you before. But these are the nice solutions for the spectra of this thing, and the wave functions look like the ones that I'm depicting here. The ground state is the one that is there with n equals 0. It has a sizable part of the wave function beyond the minus a plus a point, which is the characteristic, the classically allowed region, essentially. So, important part of the wave function for this potential well is beyond the classical limits here. What I'm saying, this region here. And then, the first one is like if this is like the sine of half of it, this is the full wave sine, so both sides. Then I have 3 things, then I have 4 things, and so on, okay? And these are the phi's, and these are the corresponding phi squares, okay? And this what this graph down here is trying to depict is that this curve, the blue curve, is the classical probability of finding the particle somewhere. How do you find the probability of finding the particle somewhere? It's essentially proportional to the length that you're looking at, the dx, divided by the velocity. The higher the velocity, the less probable you will find the particle there. And this thing, in this case, for example, here it should be divergent when it goes to A because the velocity is 0. So this thing goes up like that. And probably the particle will have the minimum probability to be found here, because here is when the velocity is the maximum velocity of the particle can have, and this position of the thing, maximum kinetic energy, which is rather contradictory with what ones get by looking at the probability distribution calculated quantum mechanically, okay? Which is not a surprise in a sense, but as soon as you start to go to higher numbers, you can see that the probability start to be more similar. In these cases, they always go to 0. There are points in the x-axis where the particles are nowhere to be found. Okay, this is it. In this case, that's it. But the average probability starts to look like the classical limit. So in the classical limit, essentially, this is a good measurement of the probability when the number n is high. When you have a very high n number here, essentially the classical behavior is a reasonable one, okay, in terms of the probability of finding the particles, in terms of the way you describe the wave function, apart from the fact that you have these zeros here, okay? And remember, you have these zeros in the probability density. Phi x is the probability density because you have to multiply it by dx and integrate over all energy ranges in order to find the total probability for finding the particle somewhere, okay? So phi x squared, you can actually name it as a probability density, okay? Let me see. I have 10 more minutes of time that I can be with you guys today. And I'm going to try to motivate looking at particles in 3 dimensions. We had this expression for the Schrödinger equation in 1 dimension. We have the kinetic energy term here with this p. This would be px squared. Vx times phi is the potential energy, which is this term, and this is the energy term. When we derive the proper thing here, we can get the stationary states that we have been describing in the last few situations. How do we go from here to 3 dimensions? It's very easy. The only thing you have to do is recognize that this thing here is equal to p squared over 2m, essentially. So the kinetic energy operator should be p squared over 2m. If I only have 1 dimension, py and px does not exist, and I produce that, and I get exactly this equation. Okay. But now I can mimic the same thing. I can write the px squared, py squared, pz squared. This thing squared, it means that I have to apply them both times over the function that I have here, phi. But this IH is simply a multiplication, and this is what gives me minus h squared over 2m. So this thing appears. So I have this this term which contains derivatives in each one of the coordinates, second derivatives of each one of the coordinates. Here I have the potential, which is essentially a function of each one of the coordinates. R is equal to x, y, and z times the corresponding vectors. The wave function, so this is the natural generalization of this equation in 1 dimension that we have already shown that it works pretty well in many cases, okay? So the good thing about this is that the 1D interpretation of this kinetic energy operator still works, and now we are looking for stationary states of this equation, so we replace what we are doing now is trying to solve this equation, or trying to get rid of things to solve the easy parts, okay? In 3D, there are no easy parts, by the way, okay? So for stationary states, we do this. We describe the wave function as phi of x, y, and z, and t as a function only of the spatial coordinates, and t is e to the minus I e t over h bar. If I take this and replace it in this equation, what do I find? I find equation number 1. This here is the Schrödinger equation in 3 dimensions, essentially. Gentlemen, you're seeing it right now. This is quantum mechanics as is best. From this solution, these things over here, this is for a particular particle solution, phi conjugate times phi integrated over all space. This is a d3r here. This is a volume integral now of this expression, or dx, dy, dz. Okay. And if you do that, the integral should be equal to 1. This dr cube here, you can write it in many ways. It depends on the symmetry of the wave function that you have here. You can write it as dx, dy, dz. You can write them in spherical coordinates, or you can write them in cylindrical coordinates. This is all good. It really depends on the symmetry of the wave function, which is the most convenient one to use in a particular case. The general solution of this equation is something that depends on time, and that dependence on time will be something like this, okay? So you will have a coefficient, a constant coefficient, times the spatial dependence that we find the solution for energy E. This is the amplitude of energy of the state with energy E, and we have the energy dependence of the state with energy E. meaning the time dependence of that. So this is the time varying part. This is the thing we have to find out in most of the problems, and this is not an easy task. As I told you before, there are 3 or 4 problems that you can solve exactly, not numerically, but algebraically in quantum mechanics. And probably we're going to see them all today, you know. And then you have to sum over all the possible values of the energy in order to get the complete solution to this equation. You fix the values of the A sub B based on the initial condition, just as you do with any differential equation. Yeah. Well, simplest problem. The problem of in 3 dimensions. Oh, I made a mistake here. No, that's okay. I thought that was the mistake is that's not T, that's a Z. Okay, it's almost evident, but okay. Simplest problem. Potential well in 3D, meaning the particle can move freely, 0 potential inside the box, infinite potential outside the box. So again, we have this we have to do 2 things here. There are 2 relevant aspects to solving this equation. The first one is separation of variables, which is a standard technique that people use to solve differential equations in 3 dimensions. And the other one is boundary conditions. What do we need? We need to define the boundary condition. There's no surprise here. The wave function in this line here, it should be equal to the wave function in this line here, and should be both equal to 0 because, you know, the potential outside the box is infinite. Okay. So the proposal is the wave function, which is a function of x, y, and z, is a function of x that's only function of x. It's a function of y, capital Y is also a function of y, and capital Z, which is only a function of z. Okay, so I get all this, I replace them in this equation, I fix the value of the potential equal to 0. I'm solving this thing inside the box. Okay, what is the potential inside the box? And I got this equation, which is equal to this, and these are the allowed energy levels outside inside the box. So I define this as k squared, a big k squared, and each one of these is kx squared, ky squared, and kc squared. So essentially, to solve this problem, I said, what I have here is the sum of this thing must be a constant. What I'm saying here is for this to be valid, always, each one of these things should be a constant independently. This is what it's called separation of variables, and I apply that here, and I find the solution that phi of x and t is equal exactly to this sign thing. How did I write this thing so fast? Well, because it's a one-dimensional problem in this direction, and in that direction, and the solution is simply the product of the 3. And the normalization should be the same, the product of the 3. The normalization is 2 over L square root. So here is 2 over L square root cube square root. Why? Because I have the product of the 3. Okay, so this is the actual wave function as a function of E or nx, ny, or nc. And the energy can be written in the same way as a function of nx and ny and nc. And this thing are quantized in the following way. Kx times L, which is this part of the solution here that has to do with the sign of Kx times x, should be equal to, I didn't even go through the intermediate step. I wrote the solution immediately because of what I know from one dimension. Okay, so this is the funny thing. Here, for example, we are looking at the density of points in this. It means that phi squared is large. Okay, so the larger number of points in here means phi squared is large here, and phi squared is large here. This particular energy level you can see how the energy levels are Nx, Ny, and Nc. So the energy for N, when Nx is equal to 1 and Ny and Nc are equal to 0, is the same as when Ny is equal to 1 and X and Nz are equal to 0. Why is that? Simply because of the symmetry of the problem. See, this, what I'm saying here, this is the plane where the actual value of the wave function is 0, and you have this sort of two lobes of the equation. Everything is 0 on the walls too, you know, but in this particular place it's also 0 because this is an intermediate symmetry plane of the wave function. And when you raise them to square, you see a lobe here and here, but you can see that you can also construct it, since the problem is completely symmetric, you can also construct a wave function that it is in the front half is maximum and in the back half is maximum. Okay, so this is just changing the index here, or instead of that, the top and the bottom, and you can realize that these three states have the same energy. Okay, have the same energy because they are produced, you know, it's simply by moving the one, all the other two of them are 0, and you move the one from one position to the other. So this is one well, it's a bit more sophisticated than that, but you have to work the details because it's not only the one, okay? Because the one, if I do it with one, it's only one lobe, okay? And I have one lobe here, and then the other has the other lobe in the other direction, the other in the other direction, okay? So this is the 1 0 0 0 1. You can see that those are the let me see. I take it back. 1 0 0 is not a solution, okay? Because if this guy is 0 and this guy is 0, the whole wave function is 0. That's not a solution. The ground state here is produced when nx is equal to ny, is equal to nz, and is equal to 1. Okay, that is the one with a one big lobe associated to the product of the three wave functions. This one over here is when this is 2 and the other two are 1s, and you move the 2 from this position to that position to that position, and you get the same value of the energy and the same value of phi squared just by changing the axis. Okay, so we call that in terms of the energy, this is called degeneracy. Okay, and here I have labeled the degeneracies of each one of the states as a function of the energy itself. I have a diagram here. Here is it. Look, all these states Nx, Ny, and Nc have the same energy. Here the degeneracy is 1. Only 2, 2, 2 is has no. What I'm saying, yes, only this one has energy 1. This 1, 1, 1, it's also something that has a degeneracy equal to 1. This guy here has these three states. These are the one that I was showing you depicting before, the 2, 1, 1, the 1, 2, 1, and the 1, 1, 2. And this produced these two lobes in the different orientations, okay? So this is the infinite potential well, and we have discovered that due to the symmetry of the problem in 3 dimensions, you can get a fact that one energy level can be produced by 2 different quantum mechanical states. And this is a very important aspect of the problem. This is what really I want you to remember, because the next class we're going to start with the hydrogen atom, and I think this is too much for today. Okay. Any question, guys? I should start giving you homeworks, huh? Yeah, because otherwise, you know, that would be unfair not to grade you better. But I don't have a homework today. So this is it. This is quantum mechanics. You've got it all now. The rest of it is a lot of work. Actually, I went through the more complicated details, and I'm trying to rescue the results of it. Okay, and most of the things are really very well worked out by a bunch of very bright people, which does not include me, and that they have proven that you can have, you know, very, very precise predictions based on quantum mechanical models. Okay, guys, I have to run. So if you don't have any questions, we could, you know, start next week with a session of questions, and not next week, next Thursday, with a session of questions, if you don't mind. Okay.
All right.
Okay. See you then, guys. Bye-bye.
Take care.
Ciao.